Hi, Mr. Richmond. This is your Integrated Math 2, Unit 16.3 and 16.4 lesson summary. In this lesson, we're going to take a look at the inverse of a function, what that looks like graphically, how to find that via the equation. Actually, that a couple different ways. And then we're going to talk about what a one-to-one function is and how, when we're looking at the inverse of a function, how we might be able to restrict the domain to keep it as a function. So let's start with what an inverse is. An inverse is basically the exact opposite operations in order that you're performing to a function. So one way I can determine an inverse operation is to work backwards and retrace the steps to return to an original value or position. For example, if I was doing 2x plus 3. Okay, if I thought about what was being done to x here, first thing that's being done to x is it's being multiplied by 2 and then added by 3. Well, if I want to do the inverse of that, and actually just to keep our notation looking right, why don't I make that f of x instead? Well, if you ask me to write the inverse function of that, one way I could do that, and the inverse function is always used using this notation, f negative 1. If it was g of x, it'd be g to the negative 1. A negative 1 exponent in math basically is a symbol for inverse here. Is I can do the exact opposite operation as what was done here in the opposite order. So rather than multiplying by 2 first, I'm going to do the added by 3 line first, but instead of adding, I'm going to subtract by 3. And then because it was multiplying by 2, I will instead divide by 2. And I can create the inverse function by doing these operations to x in this new order, in reverse order with the opposite operation. So I'm going to take x, and I'm going to subtract by 3 first, then I'm going to divide it by 2. And this creates the inverse function for f of x. So that's one way I can do it, is by basically listing out the operations being done, change the order, and do the opposite operation. Now that can get very complicated very quickly, so there are some better ways to do that we'll show you in a moment. So this new function is called our inverse function. It's a function which takes an output value and turns it back into the original function's input value. And there I have the denotation. So another way that you can do this is if you take your original function instead, let's say y equals 2x plus 3. And instead of using the function notation, I'm going to use y in place of f of x. It's a little easier this way. And what I'm going to do is just change the location of x and y. I'm going to change y to x and x to y and solve now for the y. And what this causes to happen is it allows me to algebraically see the steps necessary to isolate for this new y position. So I end up with y equals x minus 3 divided by 2, which is the exact same thing I got here. I just have to put a inverse function notation on it now. And so when it's a little more complicated, this tends to be quicker for you. Rather than try to identify all the operations being done to the x and change the order and do the opposite, I can just change the output and input variables and resolve for that. So this is most likely going to be the method you'll prefer. Okay, and that can help me find that inverse function. A composition of functions is a method of basically plugging two functions into each other for x and simplifying them down and seeing what they become. And that you'll see in example 2. I'll do that in a moment. If both the compositions simplify down to x, then the two functions you're looking at are inverses of each other. Okay? And a one-to-one function is any function where the function itself and its inverse are functions. Now you might be wondering, well, the word on function here, but what that means is there's one output for every input. Okay, that's the definition of a function. And so if I had an equation, I would check if it's a function, one output for every input, do the inverse, find the inverse equation, check if its output, if it has one output for every input. And we'll show you how to do that as well. And then lastly, let's say I did have something that was not one-to-one function, but I want to use it as a function because equations are best used when they are functions. There's only one output for every input. It makes it a little easier. What I can do instead is restrict the domain, which is, okay, I'll do the inverse, but I'm only going to use the domain of the inverse that makes sense or that works to keep it a function. Okay, and you'll see that in our last set of examples. This last bit, this one-to-one function and restricting the domain, you're going to see this more in section 16.4. Okay, the first two examples here are for 16.3. With that said, let's get started. Let's see what some problems might look like with this. So it says determine the inverse of this function, then graph the original function and its inverse. So let's start by finding the inverse function. I think the easiest way is to momentarily pretend this is x and y, and then to change x and y's position and solve for the new y. So I did that, and now I'll show in red the steps. I'm going to subtract 9 to both sides. That ends up being x minus 9 equals negative 3y. Next step, to isolate y, divide by a negative 3. And I'm going to clean up the way that looks. That would become y equals, and I need to simplify that. So I have x divided by negative 3. Well, that's the same as doing negative 1/3 x. And I have negative 9 divided by negative 3. Well, that's the same as plus 3. And so there's my new equation. It is my inverse, so I'm going to write it as an inverse. So here's my original function. Here is my inverse function. Negative 1/3 x plus 3. Okay, so I found the inverse. Now let's graph it. I'll graph the original function in black. Negative 3x plus 9, it's linear. Review of linear equations again. We have a slope and a y-intercept, and you always start by graphing the y-intercept. Let's do that here. 0, 0 is right here. I'm going to go up 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And my slope's negative 3, which means I can go down 3 over 1 from that point repeatedly. And I have my graph. So there's the original function, and I will graph the inverse function in blue, show you what that looks like. It's again linear. Slope is negative 1/3, y-intercept is 3. So I'll go up to 3 with my y-intercept, and my slope here is negative 1/3. Is that right? Yep. So I'm going to go down 1 over 3, down 1 over 3, and I'm out of room here, so I'll go up 1 over 3, up 1 over 3. And a little bit off. Let's see if I can make that look a little nicer actually. And there we go. So again, the process, I changed the position of x and y, and then I solved for y, created the inverse function, wrote it in the inverse function notation, and then I graphed it. Now, one other important point to illustrate here with graphs to make sure you have things right, well, inverse functions when graphed actually reflect, but they don't reflect in a way you've really seen yet. They don't reflect over the x or the y-axis. They reflect over the diagonal line y equals x, which basically means y-intercept is 0, sloping up 1 over 1. So I'm going to make a red dashed line so you can see how that works. So you can see there that those two lines are reflecting over that diagonal line. And all inverses should do that. When graphed properly, they should reflect over that line y equals x. So it's just a nice little check that you did things correctly if they look like they're reflecting over that slanted line. Okay, moving on. Let's say I gave you two functions and I just want to know if they're inverses. Well, I could, of course, test this by graphing each of these and seeing if they do reflect over the line y equals x. But there's another way using composition of functions. What is compositions of functions? Well, you've evaluated things before, like if I said f of 2, well, that would mean to plug 2 in for x in this equation and solve. Well, the composition of functions is just the idea of taking one function and plugging it into another. It's a function within a function. A lot of my students like to call it the inception rule, if you've seen that movie. You do a dream within a dream. This is a function within a function. I'm going to take the entire function g of x and plug it into f of x. That would be g of x. I'm going to completely plug it in for x here. So it would look like this. Negative 1/3 times, but instead of x, I'm going to put blank parentheses. And then plus 4 is outside of the x, so it's separate. And in the parentheses, I'm going to plug in negative 3x plus 12. And then I'm just going to simplify what I have here. So let's see what that becomes. Negative 1/3 times negative 3 is positive 1x. Negative 1/3 times 12 is negative 4. So I have x minus 4 when I distribute, and plus 4 at the end. Negative 4 plus 4 is 0, leaving me with just x. So f of g of x would equal x. Well, the rule that exists here is that if you can do the composition of functions for both f of g of x and g of f of x, and they both equal x, then the functions must be inverses of one another. So all I have to do now is try the other one. G of f of x. What would g of f of x equal? It would equal negative 3, but instead of x, I'm going to replace it with the entire f of x function. So now this entire function can plug into the x here and replace it with a more complicated input. So negative 3x is now negative 3 times negative 1/3 x plus 4. And now, just like I did here, it's just a matter of simplifying it. Negative 3 times negative 1/3 is positive 1x. Negative 3 times positive 4 is negative 12. Plus the 12 on the outside gives me x minus 12 plus 12 equals x. So g of f of x equals x. Since it equals x for both, they are inverses. And I can just say they are inverses because both compositions equaled x. This definitely takes practice, so you want to make sure you're doing the homework on these because there's quite a few things that can happen. When both of them equal x, it's an inverse. If only one of them simplifies down to x, then they are not inverses. It has to work for both, and that can happen where it only works for one. If it doesn't work for either, then they are not inverses. So typically, once you've tried one, if it doesn't work, you're done right there, assuming you did it right. Now, there's a lot of chances to make algebraic errors here, so you want to be careful. Check your work, check your negatives, make sure you're plugging things in correctly. So that's how I can check that two functions are inverses. Here's how I can find an inverse in example 1, and then graphing is really just graphing two equations in any way you would. You could also graph those using a table, don't forget that. You should never just leave a graph blank, because worst case scenario, if you don't know the shortcuts for graphing something, you just make a table of values and do the best you can. But we now know that the inverses of graphs should reflect over the line y equals x, this slanted line. Okay, let's take a look at the next section, which is really just going to expand on this slightly. What we're going to do now is basically try to prove if something's a one-to-one function. Is the inverse and the inverses, is the function and its inverse truly a function? Does it have one output for every input? So one way we'll kind of look at doing that is a problem like this. I'm going to give you a function. I'm going to have you make a table. Okay? In the previous examples, we wrote the equation, we wrote the inverse, and we graphed it. This time we're going to try to look at the tables and see what kind of relationships exist. So I'm just going to complete the table for f of x by plugging negative 2 in. I'm going to do this in my head because I can do it that fast. You at home might want to work it out. Negative 2 squared is 4. 4 times 3 is 12. 12 minus 4 is 8. Negative 1 squared is 1. 1 times 3 is 3. 3 minus 4 is negative 1. 0 squared 0 times 3 is 0. Minus 4 is negative 4. 1 squared is 1 times 3 is 3. Minus 4 is negative 1. 2 squared is 4 times 3 is 12. 12 minus 4 is 8. And it's a quadratic, and so this kind of makes sense. 8, negative 1, negative 4, negative 1, 8. Kind of got a vertex. Y-intercept 0, negative 4. Everything kind of makes sense there. So that's my original function. It's a parabola. Let's see what the inverse function would be. Well, one thing that you can do to get an inverse function as well when you're doing a table is truly to find this inverse function, right? All I would do is change the position and put x in the output position and y in the input position. Well, what that does is pretty much just flip-flop your table. I can actually already know the table values for this inverse without even finishing turning it into the equation. All I have to do is flip-flop my table values. If the output was 8 when the input was negative 2, when the input is 8, the output will be negative 2. When the input was negative 1, the output was negative 1. So in the inverse, when the output is negative 1, when the input is negative 1, the output will be negative 1. So 0, negative 4, if you're talking about the inverse, should be negative 4, comma 0. 1, comma negative 1 should be negative 1, comma 1, and 2, comma 8 should be 8, comma 2. So, are these functions? Well, to be a function, you have to have one output for every input. So negative 2, one answer. Negative 1, one answer. 0, one answer. 1, one answer. 2, one answer. Here, 8 could be negative 2 or 2, technically, because I have 8 in 2 spots. Negative 1 could be negative 1, but it could also be positive 1. The only one that had one answer was negative 4. So one way to check if something's a function we're looking at a table is, does the x value repeat? If it never repeats, it's a function. Here, because it repeats, this cannot be a function. So this is not a one-to-one function. It didn't follow those rules. So it is not a one-to-one function. So basically, by taking the original function's table values and flip-flopping them, you just want to check if the domain repeats at all. If it doesn't, then you have a one-to-one function. If the domain does repeat, not a one-to-one function. Let's take it a step further and kind of put all of this together now into one problem. Here's what I want to do. I have a function, x squared minus 2. I want to graph it. I also want to find its inverse and graph it, kind of like we did before. But I want to make sure it's one-to-one. I want to restrict the domain so that both my function and its inverse are one-to-one. One output for every input. And then I'm also going to find the domain and range of those. So let's start with this. I'm going to graph x squared minus 2. Okay? Now, if you know how to graph quadratics, you can do that rather quickly by doing x and f of x and plugging in some numbers, by doing axis symmetry, things like that. If you don't want to do that or you're not so good at that, you can still make a table of values and get there rather quickly as well. So I'll show the table of values to begin, but I do know some things. It's a parabola, y-intercept's negative 2, and I know that all parabolas that are x squared only are right 1 up 1, right 2 from the vertex up 2 squared, which is 4, and right 3 and up 9. So I have some shortcuts for graphing parabolas that I use. But if you didn't, you could find those points, plug them in. Negative 2 squared is 4, 4 minus 2 is 2, negative 1 squared is 1, minus 2 is negative 1, 0 squared is 0, minus 2 is negative 2, 1 squared is 1, minus 2 is negative 1, 2 squared is 4, minus 2 is 2. And you could get the first few points that way as well. I just found a few more. there's my original function. Okay, it's quadratic. Now, what's the domain of this original function? Well, it goes left forever, so negative infinity, and it goes right forever, so the domain is negative infinity to infinity. The range, low to top, lowest it ever touches is -2, but it does touch it, so it gets a bracket, and it goes up towards infinity. So there's my new domain in range. Now, how do I create the inverse function? Well, I could actually graph it really quickly by just flip-flopping these points. Okay, and I'll show that in a second. But just to make sure that we have the right equation for it, I'm going to do the typical trick we did before, make this y and x, and flip-flop their positions. So instead of it being y equals x squared minus 2, I'm going to change it to x equals y squared minus 2. How would I solve that for y? Isolate the y by adding 2 over first. And then how do I get rid of a square? Well, I square root both sides. But we know that when we do a square root in an equation, we're supposed to have plus or minus. So it would become y equals plus or minus x plus 2. And since it's the inverse function, it would be plus or minus the square root of x plus 2. So that must be my inverse function. Okay? I'm going to graph it now. Now, you probably have never graphed this before. That's okay. Even though you've never graphed something, all you have to do is choose values for x and try them. Plug them in and see what happens. Okay? Or switch your table values. Let me show you that this is going to work. I'm going to make x -2. -2 plus 2 is 0. The square root of 0 is 0, plus or minus 0 is 0. So one point on that graph is -2, 0. Well, if you look at my table value here, when the input was 0, the output was -2. So in the inverse function, that should naturally flip-flop. Now, since the input's -2, it should get an output of 0. If I try -1, I can look at my table. When the output was -1, the answer was -1. Let's see if that works. -1 plus 2 is 1. Square root of 1 is 1. And it could be plus or minus. So, hey, there's a -1 there. Okay? But wait a minute. When the output was -1, I also got an answer of +1. And so, this is where you get some issues with your table. Because if I flip-flop these completely, you're going to see that you can have some repeats. And that's where it gets a little tricky. So, let's graph the actual flip points, just so you can get a view of that. Okay, because you can see it's already going to cause some confusion for now. So, since I see that that relationship exists, let's just completely flip-flop these table values. 2, -1, -2, -1, and 2, and -2, -1, 0, 1, and 2. And I'm going to plot those points in red. Okay, 2, -2, right here. -1, -1, right here. -2, 0, right here. -1, 1, right here. 2, 2, right here. And so if you look, it's kind of odd. It's going like this. And that's because it's making a horizontal parabola. It is reflecting it over y equals x. So it's actually reflecting here. It's a little hard to see because we have some overlap going on. But it is reflecting it over the line y equals x. Now, what would the domain and range be if I kept the full function? Well, the domain is now -2 to infinity. Because it goes from -2 to infinity, and the range is infinite. -infinity to +infinity. And what I want you to notice is what happened here with the original and the new. Right? You do the inverse of a function, since x and f of x just flip-flop, so does the domain and range. The range becomes the domain, the domain becomes the range. And so I've graphed the original function and I've graphed the inverse. Now, I'm not sure exactly what all teachers and all tests are going to do. Some may have you restrict the domain, some may not. If they just ask you to graph the inverse, that would be it. Write the inverse function, that would be it. Write the domain and range, that would be it. Easiest way, graph the original, find the domain and range, make a table of values for it, because then you can just flip-flop those table of values to get the inverse function, plot it, draw it, and then now you can see your new domain and range, or flip-flop your domain and range. Okay? For this particular problem though, I said to restrict the domain so that both are functions. Well, the blue is a function. If you remember the vertical line test, that's one way of proving something's a function. It would pass the vertical line test. The red one, however, would not. I would repeat through if I drew vertical lines. So I'm going to erase the bottom half of this instead and only use this portion. This portion now is a function and should be what I should use. So what is that? Well, that's just all the positive square roots. If I made it 1, it's 1. If I made it 4, it's 2. So all that requires me to do is get rid of the plus minus and just use root x plus 2. And that's one way I can restrict the domain so that it's a function, is by eliminating the plus minus, I won't get repeat table values. Okay? So I know it's a lot to take in there. These are definitely kind of tough sections. But make sure you're working through the book. Make sure you're trying problems. This is kind of ultimately where we want to get you for Math 3, is to have this much understanding about functions and graphs and the relationship between equations, tables, and graphs. Okay? Wish you the best. Good luck.